In our first video on the Laplace transform, we had defined the Laplace transform of some function of f of t to be this improper integral from 0 to infinity of e to the minus st f of t dt. In this video, I want to study three different properties of the Laplace transform. I'm going to talk about linearity, I'm going to talk about the existence of the Laplace transform, and I want to talk about the existence of an inverse Laplace transform. For linearity, I'm going to consider the Laplace transform of some linear combination of two functions f and g. So I've got a coefficient a in front of the f of t and a coefficient b in front of the g of t. So the way this is defined is, well, I take the improper integral of e to the minus st and I put in that linear combination. It just plugs directly in. Now here's the key trick. Back in first year calculus, we proved linearity of improper integrals like this. That is, because it's an improper integral, I can go and do a similar linearity computation and rewrite this as the coefficient a out the front times the first integral, the integral of e to the minus st times the f of t, plus then the coefficient b stuck out the front of a second integral, the integral that now relates to the g of t's. And then, just by the definition of the Laplace transform, this is just going to be a times the Laplace transform of f, plus b times the Laplace transform of g. And so therefore we have our linearity claim that the Laplace transform of a linear combination is nothing but the linear combination of Laplace transforms. Now, before I talk about existence, I want to introduce a little piece of terminology called what it means for a function to have exponential order. The idea is this. It says that the magnitude of the function is eventually, for large enough values of t, simply less than some exponential function. I put an arbitrary constant m out the front and some constant c up in the exponent. But the idea is that the f of t is going to be less than this me to the ct, for at least for large enough values of t. There's a simple enough test for this, which is just take the limit. So if you look at the f of t and divide out by this exponential, is this limit as t goes to infinity going to exist or not? For example, if f of t is polynomial, so you have some polynomial of degree n on the top and an exponential on the bottom, well then, by L'Hopital's rule, iteratively we've shown in the past that exponentials always dominate polynomials, and that limit would just be 0. So yes, a polynomial is of exponential order. Now, the reason why I care about this is that there is a negative exponential in the Laplace transform. And because the Laplace transform is an improper integral, it's going to infinity in its upper limit, we really want to have convergence, and so that negative exponential in the Laplace transform is something that drags us down. The integrand gets brought down to 0. And so basically this is going to exist unless the function was more than that exponential in some sense. What I mean more precisely is the following claim. This is my existence theorem. And it says that if you have some function that's continuous with exponential order, then that Laplace transform is defined for all values of s that are bigger than c, where c is the constant that the function has when it is of exponential order. We say exponential order with constant c. So under those conditions, where your function basically is nice enough, then you get a Laplace transform defined. And to prove this, well, let me just state what the Laplace transform was. Okay, so in proving this, we really want to address why is it that being of exponential order with constant c is relevant for the existence of this particular integral. Well, this integral is an improper integral. It's got t going to infinity. But the good news is that it's got a negative exponential, the e to the minus st in it, and negative exponentials are going to bring the integrand to 0 as t is going to infinity. So the loose idea is that this is going to converge unless your function f of t was so large that it sort of undid that exponential. And this is why we want to demand that it's of exponential order. Okay, so let's see how the proof works. If I focus in precisely on that f of t, then the claim is that because it's of exponential order, I can replace that with an inequality. The f of t is going to be less than the me to the minus ct. Indeed, we're using a theorem from first year calculus that says if you have an inequality of the integrands, you get an inequality of the improper integrals. Here I can combine the two exponential terms and I can integrate them. I'm going to get m times e to the c minus s times t divided by c minus s. This is evaluated between t is 0 and t is infinity. When you plug in t equal to infinity here, Whether this converges or diverges depends on the value of the c relative to the s. But if you notice what my theorem says, it says that when s is bigger than c, we're going to get existence. And indeed, if I plug that in, when s is bigger than c, it's a negative exponential on the top. The t going to infinity goes away, and I'm just left with m divided by s minus c. This converges, and so indeed our Laplace transform exists. Alright, so that was the second property, which was existence. Now the third property I want to talk about is related to inverses. And the question is the following. If you have an f of s, if you have the right-hand side of your Laplace transform, how could you have begun it? How could you have undone that process to get the little f of t such that Laplace transform of the little f of t is going to give you this thing you're given, this big F of s? Now, we have a theorem, and I'm not going to prove it here, but we have a theorem that basically says that there is a unique answer to this process. That is, if you have a big F of s, and if there turns out to be a little f of t that the Laplace transform of the little f of t is the big F of s, then there is only one of those. Indeed, we've seen in the past when our study of differential equations that questions about existence and questions about uniqueness go hand in hand. And here, the fact that there is this unique ability to undo this means that I can actually define an inverse Laplace transform. That is, I will define a new symbol, which is the squiggly L of the Laplace transform, but to the power of -1. And then the inverse Laplace transform of some function big F of s is just that unique answer, that unique little f of t that this theorem guarantees. So in this video, we have seen linearity, existence, and then uniqueness, which paired with the idea of inverses of a Laplace transform. In the next video, I want to talk about what's going to happen if I take the Laplace transform of a derivative or the Laplace transform of an integral. And after that, we'll be set up to finally solve differential equations using the Laplace transform.